In the last segment, we looked at our recipe or our balanced equation as the source of the ratios between the quote-unquote ingredients and products. This segment, we looked at our equation in terms of molecules, and that's great and well and good and all, but a molecule is not anything that we can measure, really. So we're going to multiply up by 6.02 times 10 to the 23rd, and then each of these becomes a mole. So what we have is 1 mole CH4 plus 2 moles of O2 yields 1 mole of CO2 plus 2 moles of water. And then we can have mole ratios. For example, 1 mole CH4 to 2 moles of O2, or 1 mole of CH4 to 2 moles of water, etc., etc. And then we can use them to do the stoichiometry, which is where we want to use the balanced equation to give us some kind of numerical value. Okay? Now, mole ratios should not be new. Okay? So let's try this. How many moles of water can be produced from the complete combustion of 3.3 moles of methane? Methane is CH4 if oxygen is in excess. Well, the reason we care about oxygen being in excess is that we don't want it to run out, because if it runs out, then the whole reaction stops. Okay? So it's the same idea. Process, 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 process. Starting place will be 3.3 moles CH4. Ending place, moles of water. Then you have to let yourself think through, what is your plan? Mole of CH4 to mole of water. Do you need Avogadro's number? No. Do you need molar mass? No. Do you need density? No. Do you need blah blah? No. What you need is the mole ratio. Mole ratio you get from the equation. So the ratio is going to be 1 mole CH4 to 2 moles of water, which you will put up in the equation. Only one conversion factor. 1 mole CH4, 2 moles of water, which means you need 6.6 moles of water. Okay? How many moles of oxygen gas must be used up to completely consume 5 moles of methane? So now you're just saying, well, I'm not going to have excess. I want to know exactly how much I need to put in. Same idea. 5.0 mole CH4, mole of O2. Let yourself think through a plan. Mole CH4 to mole of O2. You do not need any of these tools from your toolbox. What you need is the mole ratio. Whenever you go from one substance to the next, mole of A to mole of B, or mole of B to mole of A, you always need the mole ratio. That's the only way you're going to make that happen. And mole ratios always come from the balanced equation. 1 mole CH4, 2 mole O2. That's your mole ratio. And so you have to choose, does the 2 go in the numerator or does it go in the denominator? Well, you let the units do the work for you. 1 mole CH4, 2 mole O2. Units will cancel, and you end up with 10. Now this has 2 significant figures, so I need 2 significant figures here. Okay, Now again, as I've been doing, practice, pause, textbook. You have to work on problems before you move on. So if you were having trouble with what you did out of the book, this should clarify things for you. Okay, so you can go back, try those again, try more in your book, try whatever you've got on Blackboard, whatever classroom activities we're working on. This is where you want to pause before we move on. Now, moving forward, this is all great and well and good and all, but the problem is you can't read moles on a balance. It just doesn't give you that unit. So what you have to do is use the practical unit, which is a gram. So we need a way to express our equation in terms of grams. Page 15. If we're going to start using the gram, now we're going to go from gram to mole or mole to gram, which means we need molar mass. Molar mass, remember, we get from the periodic table. Okay, so let's try an example. How many grams of carbon dioxide are produced from the complete combustion of 108.0 grams of methane with excess oxygen? Again, this tells us that we don't have to worry about this. Starting place, 108.0 grams of CH4. Ending place, grams of CO2. Our plan is that in order to get from A to B, we always have to go through the mole ratio. So we're going to go grams of CH4 to mole of CH4 to mole of CO2 through the mole ratio to grams of CO2. Make your plan. The mole ratio is 1 mole CH4 to 1 mole CO2. Molar mass, you're going to want to get that from the periodic table for the sake of this segment and not going over 10 minutes. Our molar mass of CH4 is 16.0 grams per mole, and our molar mass of CO2 is 44.0 grams per mole. So you're going to want to verify that. Okay, so now let's plug in. 1, 2, 3 arrows means we're going to have 3 conversion factors. Grams of CH4 needs to cancel, so 16.0 grams goes in the denominator. And now we've completed that. 1 mole CH4, 1 mole CO2. That's our mole ratio, which we get from here. 44.0 grams of CO2, 1 mole CO2. We push some buttons on our calculator. We round to 3 digits, 4 here, but 3 here and 3 here. And we should get 297 grams of CO2. Okay? In the next segment, we'll move along and we'll try a new reaction.